Hello everyone. During this lecture, we are going to talk about bioplastics or green plastics, which is lecture 25. Plastics leads to white pollution. Okay, so white pollutions have two negative effects on the environment: visual pollution and potential hazards. So these graphs are very representative, right? It shows how the plastic rubbish actually changing the world, right? And also impact the living organisms on Earth. So why are we still using plastic? Because they're less expensive, and also they have properties other materials cannot simply replace. And if you look at the consumption of plastics, North America is the #1 consumer of plastics. If you look at how plastics are produced in the US, okay, so 1/2 of the plastic used in packaging, and then goes to transportation, okay, and also agriculture. So, for example, as the plastic ground covers, okay, because of the environmental concern, okay, so we recycle plastic products, and also depends on the type of plastic, okay. So you see the identification code for recycling, okay. So for example, if you see the number 4, which tells you the plastics produced based on the low density polyethylene resin, okay. So this is the reason why if you check the plastic containers you have, okay, so you can actually find the recycling code. So this way, when they're being recycled, so we know, okay, these are the same, made of the same material, so they can be reprocessed together, okay. So again, this code are for recycling. And also interesting thing is, for example, your Coke bottle. So the bottle itself and the cap actually are made of different materials, okay? So even we talk about recycling more and more, there are still challenges, okay, for recycling. So as I mentioned, it is time, effort consuming, right? Especially if you have to separate them right after recycling. And also I mentioned for the Coke bottle, for example, it's actually the bottle itself and the cap actually made of different materials. You have to separate them, okay? So that makes recycling challenging. And also, for some of the plastics, you cannot simply recycle, okay? A lot of times it's not really cost effective to even recycle. So that's why for a lot country, including US, try to push down on the consumption of traditional plastics, okay? So in China, they banned plastic bags a long time ago, okay? So especially the thin plastic bags, okay, which you cannot really use for a long time, okay. And also, if you really want to use plastic bag, they actually charge you, okay, to discourage people of using plastic bags. I know for US, for some states they are pretty strict, but in general, plastic bags still widely used. For certain stores that offer options, right? They ask you, oh, you want a paper bag or plastic bags. So for plastic bags, we know the issue is because they're not really degradable, right? So study shows some plastic bags, if you just simply dispose them in the landfill method, okay, so they are not degrading, okay, for 100 years, okay. So we definitely cannot just fill our land, right, with plastics, okay. So here I have a couple videos to show you. So the first one try to tell you not all the plastics can be recycled, okay, for different reasons. And also the second video is related to new ways, okay, of processing, get rid of the plastic waste.
So good. There's no food waste here. Too tasty. What about all this container waste? Glass bottle?
Give me a second.
Plastic cup? Recyclable. But what about this styrofoam bowl? Trash? So good. There's no food waste here. Too tasty. What about all this container waste? Glass bottle? Recyclable. Plastic cup? Recyclable. But what about this styrofoam bowl? Trash? Turns out it can be recycled. So why don't we? Stick around. Hey everybody, Sophia here. We recycle glass, paper, plastic, so why not styrofoam? Well, styrofoam is actually Dow Chemicals' trademark name for extruded polystyrene, which is not used in consumer food products. Expanded polystyrene, or EPS for short, is what this container is made of. It's a close relative of Dow's material. EPS comes in a hardened state, like this disposable cutlery, or in a foamed state, like this coffee cup. So if it's made from plastic, can EPS be reused or recycled? The short answer, yes. The long answer, no. Okay, both of those were short answers. Really though, it's just not economical. In fact, this March, New York banned all EPS food service products, joining about 70 other US cities. Although contractors for the New York City Department of Sanitation argued that they could collect and recycle EPS, the city decided it wasn't cost effective. So why is this foam so expensive to recycle? Well, there are three main reasons. One, recyclers want their products clean, dry, and intact. Food service EPS is none of those things. The recycling facility would have to wash the foam within 24 hours of it going to the trash to prevent food residue from getting all putrid. Two, more than 95% of the final foam material is air. That makes it lightweight and great for insulating hot food and beverages. What that also means is recyclers would have to cart all this space-hogging material to their facilities, only to squish it down to 1/40th of its original size. Which leads us to three. In order to make this operation cost-effective, you need a lot of EPS. There's about 250 million tons of municipal solid waste in the US, and less than 1% of that is polystyrene, both in the hardened and foamed states. A huge chunk of polystyrene disappeared from our waste stream in 1990 when McDonald's stopped selling Big Macs in foam clamshells. Remember those? While some think New York City lost an opportunity to recycle more, others point out that the cost of separating EPS, shipping it, cleaning it, processing it, just wasn't worth the money and effort. So this is going to the garbage, and now I'm craving a Big Mac. And maybe a date with Mac tonight. Look it up, kids. And likely adults, because Matt Davenport is the only one who remembers him. That's all the time we have for this episode of Speaking of Chemistry. Don't forget to check out the articles that inspired this episode.
Okay, so go to our second video.
It should come as no surprise that as a species, we generate a lot of waste. Now, not all of that waste is inherently bad. Much of it is food waste, which will happily degrade in a month or two. It's the circle of life that we're used to. But not everything can be broken down in a short time. Plastics, for example, if left in the ground, will take hundreds or thousands of years to break down. One such plastic you're all probably familiar with is styrofoam. It's used in all sorts of packaging and insulation applications, and you probably had some in your holiday presents or in the cups and plates you may have used at your office party. But about a third of our landfills are filled with styrofoam, which is a crazy amount when you think about it. So obviously we need a better way to deal with this than just sticking it in a hole in the ground. For those of you who've ever had a pet reptile or other insectivorous animal like koi, may recognize these guys. They're superworms, or Xephobus moria. People often make the mistake of calling them mealworms, but mealworms are a totally different species. Both mealworms and superworms are the larval stage of a darkling beetle. The confusion arises in the fact that the Xephobus look like a giant version of the much smaller mealworms. The beetle stage of the two species look totally different though. So when a paper came out showing that mealworms would not only eat styrofoam, but were somehow able to break it down, I immediately was interested. Conveniently, my friend asked me to watch his lizard for him over the holidays. So I told him about the paper, and when he dropped off the lizard, he brought some extra superworms so I could try it out. Now, the paper specifically talked about mealworms, so I had no idea if superworms would behave in the same way, since remember, they're a totally different species. So to get a sense of how quickly they ate, I put 5 superworms in a large glass jar and added a 1.5 gram block of styrofoam. Within seconds, they went straight for the styrofoam and started eating. What's cool is you can actually hear them eating the styrofoam because it crackles as it breaks in their little mandibles. After 24 hours, you can see that just 5 worms had actually managed to get all the way through the block. 5 worms are great, but they can only do so much. So now that I know they have no problem eating it, I added 25 more worms to speed up the process. After a day, they were starting to make serious progress, and each day after that, they kept going. They take sort of a synchronized break every few hours for a few hours. Then sort of all at once, they all start eating again. Because styrofoam has no water in it, I would spray the jar with a few squirts of deionized water a couple of times a day. If I spray some on the styrofoam, I can get them to start eating again whenever I want, and they'll try and climb up the walls and have a drink before going back to eating. After a week, you can see the styrofoam is a husk of what it once was. Even after the first day, I started to notice little white bits in the bottom of the jar. As they ate, the pile got larger. However, during what I thought was a break, I noticed them eating it. I know the idea of something eating its own poo is gross to us, but this is actually really common in nature. We have really long digestive tracts filled with different kinds of bacteria so we can get the most nutrients out of our food in one go. These bugs only have a very basic and straight digestive tract. And remember, all they're eating is styrofoam. It makes sense that it could take a couple of passes to actually break it down. Over time, the color of the powder changed from white to more beige. This is a clear indication that it is actually being broken down, and I know what you're thinking. Couldn't it be remnants from what the worms were eating before I put them in there? Well, maybe in part, but the stuff seemed to go in cycles of white to beige, then fresh white, and repeat every day or two. So they were systematically deconstructing and breaking down the plastic. But what is actually breaking it down? Is it the worms? Well, probably no. In the original paper, they point to bacteria living in the worm's digestive tract. And this isn't really surprising. Bacteria are incredible at breaking things down. Back in 2009, the then teenage Daniel Bird isolated bacteria that, in high concentrations, could break down high-density polyethylene, the stuff used to make plastic shopping bags. So after a week, I did a weigh-in on the plastic to see how much they ate. After checking to make sure all the worms were out, the final weight came in at 0.8 grams, down from the original 1.5. The chunk was about 86 cubic centimeters originally in volume and weighed originally 1.5 grams, so it had a density of about 0.018 grams per cubic centimeter, or 18 kilograms per cubic meter. So, if they ate 0.7 grams of styrofoam in a week, they ate about 38 cubic centimeters. If we were to do this industrially, we wouldn't be using 30 worms. We'd be using more like a swimming pool worth. Let's say that conservatively you're going to use 1 million worms. You'd be able to process cubic kilometers of the stuff in a couple of weeks. And since they can live for about a year, that's a lot of styrofoam. And all that is from a single batch of worms in our theoretical recycling plant. A proper facility would have multiple pits. This could be a great addition to current recycling plants. They would churn out usable soil, and in theory you could eat the worms, but I wouldn't advise it. If nothing else, this needs to be explored at a larger scale and could well be an easy solution to a global problem. Well, that's all for this video. I hope you've enjoyed. If you
Okay, so what do you think about this particular, right? So this also offers us, maybe we need to look, think outside the box, right? Right? So think maybe use other ways, right, to get rid of the plastic-based waste or recycling. We already touched on the plastic degradation. Okay. So degradation polymer may occur during synthesis or in the fabrication process. So for plastics, if we look into their degradation behavior, we use the performance integrity, okay, to indicate how physically intact the plastic is and how resistant it is to degradation. So for the top left, we can see the plastic in general non-degradable, right? You can see with time, Pi the same. For the one on the top right, so this is readily degradable plastic. We can see after a certain time, we fully degrade it. And the bottom left, this is a programmed degradable plastic, so easy to understand. And also for the bottom right, so we can see the degrade curves right of the programmed degradable plastic degrading in 2 stages, different rate. There are different types of degradation when it comes to plastic degradation: photodegradation, oxidative degradation, and hydrolytic degradation. So photodegradation, we know we're talking about sunlight, right, on a specific light source. Oxidative degradation we know is caused by oxidation, for example, from oxygen. Hydrolytic degradation is a result of hydrolysis. So here shows a table of some biodegradable polymers. If we look at biodegradation, okay, it is chemical degradation brought by the action of naturally occurring microorganisms such as bacteria, fungi, and algae. So the second video is related to biodegradation. We also have mineralization. So it is the conversion of biomass to gases, water, salts and minerals, and residual biomass. Okay. if we look at the details of degradation of plastics, okay, so we know different degradation routes, okay, can occur the same time, which is simultaneous, or occur consecutively. Now, chemical changes within the plastic can occur and may begin with abiotic degradation. So biodegradation is generally considered as consisting of both enzyme catalyzed hydrolysis and non-enzymatic hydrolysis. The degradation rate depends on the environment, okay, which plastics are placed. For example, temperature, moisture level, they all affect the degradation rate. We know, for example, low temperature strongly inhibits degradation. Moisture supports hydrolytic degradation. So that's why if you expose the plastic into higher temperature rate with high moisture, they are going to have relatively high degradation rate. Besides the environment, we know degradation also depends on the chemical composition of the plastic. Okay. So first part is the four most commonly used plastics, for example, PE, right, PVC, PPS, they all have the carbon-carbon single bonds in the backbone. So the carbon-carbon single bond in general leads to hydrophobic molecules, so they are polyolefins. So because of the hydrophobic nature, they are particularly resistant to degradation. Okay, so now we know first point we can get is if the polymer contains the carbon-carbon single bonds in their backbone, they tend to be hydrophobic and tend to resist degradation. On the contrary, if the molecules contains hydroxyl groups, we know hydroxyl groups can involve in hydrogen bonding, okay? So which increase the hydrophilicity. So which promote degradation, especially through hydrolysis. The third point is the morphology of the material. When we talk about morphology of material, we can look at surface area and the degree of crystallinity. Okay, so what we know is the oxidation of polyolefins occur mainly in the amorphous region. So then, we know to summarize the surface area and the crystallinity effects. So if we increase surface area, okay, and decrease crystallinity, which will lead to the increased degradation rate. Okay. So the larger surface area, of course, right, provides a larger area for different degradation mechanism to occur, right? And also for crystallinity. We know the amorphous crystal regions that have different rate. so decrease the crystallinity, for example, which will increase the oxidation rate, leads to the increased degradation rate. The last point is for certain polymers, okay, they tend to go through hydrolytic degradation. So for example, polyesters. So for this polymer, the ester groups are separated by CH2 groups. Okay, we're talking about backbone mostly. So for this one, if we look at ester bond here, okay, so we now under hydrolysis, so the water molecule here come here, right? Break the ester bond here. So what you have is on the left side, it became a carboxyl group. So on the right side, it became a hydroxyl group. So this is the simple way to show what happens during hydrolysis. So basically, the water is split into hydrogen plus hydroxyl. Hydroxyl go left, hydrogen goes to right. So this is the easy way to explain. Okay. So these are the 4 points. Explain how chemical structure, composition impact the plastic degradation rate. Now let's talk about the bioplastics, right? So bioplastics, basically biodegradable plastics. So for them, their components are derived entirely or almost entirely from renewable raw materials. Okay. So for bioplastic, of course, they are polymer-based, so that contains one or more biopolymeric substance as their essential ingredients. In nature, biopolymers are plasticized by components in their immediate surroundings, but other additives can enhance their properties for bioplastics production. So here is the equation for bioplastics. I know for engineers we like equations, right? Here it is, bioplastics equals biopolymers plus plasticizers and other additives. Okay. So how do we produce bioplastics? So which is very similar to the ways when we talk about biopolymer manufacturing, right? So we can directly get to the plastics, right, processed from polymers from nature, for example, starch, okay? So we can make blends, for example, starch can be blended with PVA, polyvinyl alcohol, and also we can modify starch chemically to make them have different properties, and also we can get the bioplastics from polymers produced commercially in large-scale fermentation processes, which we know is direct biosynthesis, or we can use plastic processed from resin polymerized from naturally occurring monomers. Okay. For example, PLA-based bioplastics, we know we can get lactic acid, right? And then go through polymerization, get PLA. So for PLA, and the interesting is it is insoluble in water. has good moisture and grease resistance, but it is degradable in seawater and other environment. Okay, so this also brings an important point. Even we want a biodegradable material, doesn't mean the material should not be stable. That should still be stable, right, for a certain time, certain length of time, and then eventually degrade. Okay, so do not confuse biodegradable products to unstable products. That's not the same thing. So at least during production, right, use, the product has to be stable. Since we talk about bioplastics, okay, there one topic I want to talk about, the microplastics. Okay, so this is a hot topic. We know the shampoo body wash, okay, not long ago, so there was a trend that tend to add the microparticles, right, inside, but they got banned, okay, a few years ago, especially if the particles are not biodegradable. So why we care about those microplastics? Okay, so here is a recent report. I uploaded it onto the Blackboard, so we can go through this together quickly. Just to highlight certain points. So the title tells you the microplastics are ubiquitous, not just in the ocean but also on land and in freshwater systems. Ubiquitous means existing or being everywhere at the same time. Okay? So for microplastic, we are talking about the plastic particles less than 5 millimeter in size. Okay? So it is estimated about 80% of the microplastic pollution in the ocean comes from land. And the rivers are one of the dominant pathways for microplastics to reach the ocean. And also scientists reported that presence of small plastic particles in the ocean as early as 1970s. Okay. But the research into their distribution and impacts effectively began in 2004. You can see it's pretty recent. And also from microplastics, it's not only the example I gave you from body wash, right? The particles, it can also be from wearing, right, of the bulk plastic material, or from degradation of a certain plastic product. So I just make it clear, it may not be directly from plastic particles, it can be from traditional plastic materials. Okay, the plastic particles themselves are only one part of the cause. For microplastics that were first reported in freshwater in 2013. Okay. The microplastics are common in freshwater systems at a global scale. Okay. Although contamination tends to be greater near large population centers, microplastic often in the form of microfibers and being found in remote locations. Let's go to the next page. So soil can act as an important long-term sink for microplastics. So the plastic microbeads from personal care products, like I mentioned, shampoo, body wash, and so on, were first reported in freshwater Laurentian Great Lakes, leading to legislation aimed at eliminating this resource of microplastics in several regions, including United States, Canada, and other regions. So we know for Milwaukee we have School of Freshwater Sciences at UWM. So I visited them a few times. So they actually study microplastics impact on the ecosystem, especially in Great Lakes. Okay, so for their work, they also realized the significance of increase in the awareness of microplastics impacts, okay, on the ecosystem. So they study how, for example, how microplastic influence the different aquatic species within the Great Lakes, okay, and also we know eventually the water might come back to us, right? For example, as drinking water. Okay, so somehow we are indirectly impacting ourselves. So now I notice for personal care products, they actually will come back with particles, but they claim the particles are biodegradable. Okay, so if the particles are not degradable, in general, they are not allowed to be sold anymore. Last part, I want to go to our last lamp demo, okay, related to bioplastics. So which show you actually you can use starch and vegetable oil to make bioplastics. So for this demo, you can actually conduct at home or your dorm room.
Hi, this is Erin from the Science Off Center team here at the St. Louis Science Center with an experiment you can do at home. Today we are going to make cornstarch plastic. So plastic is made from polymers, and we can whip up some of those polymers by heating up the chemicals in corn. So what you'll need is some cornstarch, some vegetable oil, some water, and then a couple holding and scooping things. So you'll need a Ziploc baggie, and you'll be mixing equal parts cornstarch and water. So any amount will work. I recommend a tablespoon, which is about 2 big spoonfuls. And then the same amount of water. And you mix that together. If you've made oobleck before, it's similar to that, but this has more water in it, so it'll be waterier. Let's see, so you get that much together, and then we're going to add just a couple drops of vegetable oil. So just 2 or 3 drops is enough, and mush that in there. And then we're going to microwave this for just about 20 seconds. And the trick is that you don't want the baggie to be sealed all the way because it could pop in the microwave. So make sure it's open part way, and then put it on a plate or a bowl or something so that it doesn't leak out. Take it to the microwave and see what happens. Be careful careful when you take it out because it can be very hot. So you can see that the texture has changed. It's gotten hard, and we'll wait for it to cool a little bit, and then you can, once it's cooled down, you can start to fiddle around with your cornstarch plastic.
Okay, so try to produce some starch-based bioplastics at home, and of course you can add food dye, right, to make them different color, and also make them different shape, and also to improve the properties of these bioplastics. You can also use acid and base to modify the starch. Okay. So in general, for these bioplastics, they're kind of brittle and doesn't really have good mechanical strength. Okay, just a demo to simply show you. It's actually possible to generate more green plastic products or bioplastics. Okay, to gradually replace traditional plastics. Okay. One thing I want to mention, so we know during the video, they also use vegetable oil, but very small amount, okay? So if you do this at home, make sure only add a couple drops, not a lot of vegetable oil. So what do you think is the function of the vegetable oil? Think about this for a few seconds. What's the function of the vegetable oil? The vegetable oil serves as the plasticizer. Okay. This is all for this lecture. Okay, see you next time.